So, vanakkam. So, we will continue our lecture on engineering seismology. So, we almost came to the end of the course. So, today class we are going to talk about the different method of seismic hazard analysis and then a typical calculation. So, with this we will be finishing our course. So, we have seen that the selection of the seismic steady area, try to collect a seismotectonic details like source, active fault and mapping them and prepare a seismotectonic map by considering the seismic steady area radius based on the past earthquake. We also discussed about the seismicity data and homogenization and declustering of data and the max estimation, and then followed by the distance, okay, how to take a d minimum for hazard calculation and recurrence. Okay, so model development which is required for the PSHA analysis, and the max estimation also we discussed, followed by the GMPs, okay, different ground motion prediction models available, how to qualitatively you can take the GMPs, okay, so then how to select a GMPs considering the quantitative approach, okay, log likelihood method efficacy test. Okay, once you select a GMPs, the next part is estimating the hazard. Okay, so why we need to estimate a hazard basically? Okay, the seismic hazard account a damage of the property and life due to the occurrence of the earthquake. So, the seismic hazard analysis rationally estimate a possible seismic scenario at a site of interest due to the future earthquake, taking into account of the past seismic event in the region, available seismic sources in the vicinity region under consideration. The final outcome will be hazard map representing the value of PGA of the site of interest, or intensity if the risk assessment is required, or duration if the duration related parameters are interested. Provide input for estimating the different earthquake effect such as liquefaction, ground shaking, site response studies, also useful for designing the structures in the region. Okay, this is the broader one. So, the hazard analysis actually has a two classical method. Okay, one is the deterministic seismic hazard analysis, another the probabilistic seismic hazard analysis, which is called as a DSHA and a PSHA. Okay. So, then we actually developed a new approach called a rupture based seismic hazard analysis. Okay, rupture based seismic hazard analysis, which can be done deterministic and probabilistic by considering a regional data. That is very important. So, this sometimes does not talk about anything, some of the parameters, but here we will specify what is the parameter, how you should account a regional variation in the hazard analysis. So, that is the difference. So, today class we are going to talk about all this method in detail. I will be showing a typical calculation for this as well as this. The PSHA procedure basically you need a MATLAB based approach. Okay, so where you need to run a MATLAB code and understand a MATLAB code. As I told you that our course is only to the +2 level. Okay, so we are not going to the PSHA analysis discussion, but if you are keen and interesting on that, so we can help you if you approach us. Okay, but otherwise as per DSHA concern, rupture based one, conventional one will be sufficient. A typical example also shown in this class. So, we have seen that the DSHA, okay, approach, the earliest approach where they developed in the first. So, where they are basically developed this for the nuclear power industry application, but still it is being used for the very important structures like a nuclear power plant, dam, large bridges, hazardous waste containment, disposal sites, and this gives the cap, okay, value for the PSHA. When you do PSHA, where you can cap means the DSHA results would be important. So, that means any region you should not only do one analysis, you should do both DSHA as well as the PSHA. Typically one or more earthquake are specified by a magnitude and a location of the to the site. That earthquake is considered as a worst scenario earthquake or critical earthquake for the site. Usually the earthquake are assumed to occur portion of the closest, okay, to the site, portion of the source, okay, the distance will be closest to the site. The site ground motions are estimated deterministically by giving magnitude and source to distance and site condition. Okay. So, since our hazard analysis talk about only on the bedrock level, so there is no site condition, one only talk about the magnitude and the distance if the source parameter, if the GMPs are included, that as this one. So, consider worst scenario earthquake for arriving the hazard value without considering the possibility of level of ground motion within the design of structures. It does not give the range of ground motion, it gives only one ground motion. The event assumed to occur at the closest distance from the site accounts for the largest possible earthquake magnitude to be occurred on the fault. Okay. So, basically they have to get account largest possible magnitude to the occurred on the fault. The result obtained are highly uneconomical. Okay, because it is the worst scenario, it may happen, it may not happen. Generally useful for the important structure where the safety of the structures is the prime important, not the cost involved on the construction, particularly dam, nuclear power plant and a big bridge connecting a two regions kind of things. Those are all the place where the DSHA has to be adopted. So, the DSHA procedure, the classical textbook procedure. So, this is your site. Okay, they take a different source 1, source 2, source 3 and a different magnitude reported on that, and then they estimate the closest distance which is perpendicular to the site. Okay, then they estimate the PGA variation with the given distance, and then they take, okay, whichever giving the highest value will be the controlling earthquake that is recommended for the design. Okay, that magnitude and R and the PGA value will be recommended as a parameters for the design. So, this is the typical classical DSHA method. So, here this is like a scenario. So, if you do all this calculation, you will end up in the one earthquake, okay, for the scenario commonly used to produce worst case scenario. DSHA provide no indication how likely the design earthquake to occur of the lifetime of the structures. It may occur, it may not occur, but it is a worst scenario. The design earthquake may occur every 200 years, some places every 10,000 years, in others as we have seen that some of the places earthquakes are frequently occurring, which is plate boundary regions. Some of the places it occurs once in a while where the interior of the plate or mid plate. So, that kind of interval considering the worst scenario will be the too much of investment. Okay. So, DSHA can require subjective opinion of some input parameters, variability effect are not rationally accounted. Okay. So, DSHA approach uses the known seismic source sufficiently near to the site, available historic seismic record, geological data to generate discrete single value event and model up from the site. Okay. It gives a single value from the known magnitude and the distance based on the available data. So, the summary you can make say that typically one or more earthquakes are specified by a magnitude and location with respect to the site. Usually earthquakes are assumed to occur on the portion of the site closest to the site. DSHA calculations are relatively simple, but implementation of procedure in the practice involves number of difficult judgment. The lack of explicit consideration of uncertainty should not be taken to imply that those uncertainties do not exist. DSHA calculations are relatively simple, but implementation wise it is very expensive. So, in order to overcome that, the probabilistic seismic hazard analysis has been developed, okay, where they try to consider the uncertainty associated on the different parameters or component of the hazard analysis and try to quantify that uncertainty mathematically. Okay. So, then they give by asking a owner how much risk you want to take. So, I want to take 50% repeatability. Okay. So, then 25% or so based on that you will get a hazard value, okay, how much risk you want to take. So, which basically manages a cost and risk you want to get out of this. Okay. So, this because of that this is more useful for the buildings, because the building life is basically 50 years, okay, or 30 years or 10 years. So, depends on that you can take a, okay, I want to take short structure more risk, okay, less risk and long structure, something like a different combination can be worked out in the PSHA procedure. So, this was developed by Cornell, okay, in 1969 paper. So, where he assumed that, okay, so since we do not know where, when and how the earthquake going to occur, so he assumed that all the possible magnitude, all the possible distance, all the possible effect of the earthquake, so that the PSHA characterize uncertainty in the location, and size, frequency and the effect of earthquake and combine all of them, okay. So, to compute possibility of different level of ground shaking for the analysis. So, the location is basically a distance, okay, site to source distance. So, you take a probability density function of the distance and size, magnitude, okay, the minimum maximum magnitude possible and consider all of them, and the effect, okay, how this magnitude and distance combined in the GMPs, and then how these values are varies, how the error term is there, and then the time Poisson distribution model is used to account a time. So, we will discuss these steps in detail. So, one by one. So, this all this put together and then say that, so the combining all the uncertainty of the this one and each one and then combined like this and say that an minimal, okay, rate of exceedance of particular PGA for the given probability of exceedance. So, that will be estimated, that estimation will be done using the loop, okay. So, like the repeatability of the sum of the steps again and finally you arrive at summation values by varying the parameters. For example, as I told you that the minimum and the maximum distance, they take minimum distance and then vary up to maximum distance each and every segment, okay, saying that my earthquake may occur here, then here and then here and then here and then here, and what is the probability density function on each one and what is the possibility of occurring, that is modeled in the probability density function. So, this basically, so you will get a PDF of the distance like this using the functions which is described in detail, okay. So, in some of our publications also you can see, and you get a variation. So, if you have the aerial source, you will be taking as a grid, different grid like this, and how this grid distance are varies, okay. So, like that you can take and then you can get the this one. So, you can see the aerial source, how the center is divided, how the distance, the uncertainty associated with that. So, linear source is very easy. So, aerial source you have to make it as a square grid and estimate the probability density function. So, basically which implies that a particular fault, okay, a smaller and a bigger magnitude can take place at a different distance. So, each distance you will be estimating what is the probability of occurrence, you can see that. So, this is the fault, this is the rupture length. So, with this rupture length keep moving from this point to this point, and what is the probability when it moves from different segment, which is explained with the dimension given here in this equation. So, you have to model this and estimate this for your site case, that is what doing in the probability, so occurrence of the distance, okay, probability of occurrence of the particular distance. So, this is the typical probability so distance for the given site, okay. So, the next basically is the magnitude. Once the distance is defined, so the magnitude, the low magnitude and largest magnitude, the largest will be the M max, okay, which is occurred based on that, or you can estimate by any method, and then take a Gutenberg-Richter relation, because the repeatability of the magnitude depends upon the recurrence relation with the AB parameters. So, combining both you can estimate a magnitude, this one. So, how small and big magnitude can be expected on the same location, how the probability density function varies or the cumulative effect of this magnitude varies can be modeled using this equation. Here you can see that the alpha, okay, and B value, okay. So, those are all the function of your Gutenberg-Richter relation, and that is developed for the entire region AB value, which you can narrow down to the your particular source by doing a de-aggregation by considering the your length of the source, total length of the source in the region, number of earthquake in the particular source and total number of earthquake. So, this de-aggregation will help you to narrow down your recurrence model from regional or a entire seismic steady area to the a particular source, okay. So, that is very important. So, that will help you to get a magnitude uncertainty in the particular place, okay. So, this calculation has to be done in MATLAB kind of coding, because it involves the large number of repeatability of the steps, okay, looping of step. So, that needs to be accounted in the proper calculation tool, okay. So, the next, once you are done with the magnitude and distance, next you are going to use a particular ground motion prediction equation. So how the ground motion prediction equations are reliable, what is the error associated with that, that uncertainty is estimated on the using this kind of phenomena. For example, different M and X combination will give you the GMP PGA, that PGA may varies functionally with the real value. Okay, how the known value and the estimated value will varies with the this combinations. So that uncertainty is estimated using the predictive equations. Okay, so like this has been modeled, as you can see that the combination of y and this one. So what is the probability density function. So similarly the y for a different way. So this uncertainty is modeled, okay, in the PSHA as a ground motion prediction equation uncertainty. So after this is the temporal uncertainty, like time. Okay, this time, as I told you that the Poisson model is used. Okay, the number of occurrence of one time interval are independent of the number of that occurred at other time interval. Probability of occurrence is very short time interval proportional to the length of the interval. The probability more than one occurrence at very short time interval is negligible. For example, so this is the Poisson process where you take that 1 minus EV into Z by T. So that time T is actually the average number of occurrence time interval interest, n is the number. So you can take that, typically how this probability works basically. So what is the probability of the occurrence of at least once in 100 years? So you consider a event which is occurring average of every 1000 years. So what is the probability of occurrence in 100 years? So like lambda is equal to 1 by 1000, which is 001. So the P is 1 minus exponential of lambda and T. So that is what here you are given here. So you can see that you get this one. So this is the probability of occurrence of in 100 years. Okay. Similarly, what is the probability of it will occur at least once in 1000 years? You can see again same you can get. So even though it is once in 100 years we said occur, the probability of occurrence is actually 0.63. So the probabilistic based approach, that is where they have incorporated. They do not give 100% weightage there, but they give the mathematically considering the structure. So here they also annual rate of exceedance on an event with the 10% probability exceedance in 50 years. These 50 years corresponding to the structure. Okay. So the lambda is equal to ln of 1 minus the probability like this whatever, and 50 you get this is okay. So the inverse of that is actually their return period. If you make a 2% probability you get a 275. So that means the 10% probability if you take any event occurring on the 475 return period is accounted in your design for the period of 50 years structural period. Okay. So this typical calculation you can try to understand. So similar way you can also work out for the 2% probability in 50 years, this is the calculation. So this model, okay, all these models are combined here, okay, the temporal variation, okay, distance variation, magnitude variation and GMP uncertainties are combined together, and finally the mean annual rate of exceedance is estimated with respect to different period of the structure and the different PGA value. So that is called as a hazard curve. So the mean annual rate of exceedance is plotted here with the spectral acceleration like PGA of the different source you can estimate and different period you can estimate considering the G value variation. This typical curve is called as a hazard curve from the probabilistic seismic hazard analysis. So this curve can be also estimated for the cumulative curves actually, okay, by considering. So this curve actually has a different shape for a different region. You can see intraplate how it varies, okay. So the interplate, intraplate and then crystal, you can see how this varies. This is the general trend observed. So similarly this is for the peak acceleration. For the spectral acceleration at 3 seconds, you can see the shape difference. Okay. So this will give you the mean annual rate of exceedance. So the inverse of this is actually a return period. Okay. You will know that what is the approximate return period of a given G value. Okay. That will get on the right place on this one. So if you estimate a given response spectrum for similar probability of exceedance, okay. So that means you keep your probability of exceedance lambda value, okay, and the period of structure same, and try to estimate how the spectral response varies for the different period. That is called as a uniform hazard spectrum. Okay. So this uniform hazard spectrum similar to response spectrum, but it is for the given constant probability of exceedance. Okay, that is the difference. The response spectrum is response of single degree structure for a given input motion. Here the given constant probability of accident, how the spectral acceleration varies. Okay, that we will get from the uniform hazard spectrum. So this can be done, okay, where you can see the typical hazard curve which we have developed for several projects. So different source you can see how the mean annual rate of accident and then the cumulative of the particular region. So generally the cumulative will be taken. And source wise if you take, you can see that which source is giving more, okay, that understanding you can do in the hazard analysis. You can also estimate and different area of the steady area how the PGA varies. This is the typically 2% probability of accident PGA at Bangalore, 10% probability of accidents in the 50 years. You can see the difference. So generally 2% will have the higher values. You can see the when compared to the 10%. Okay. So this PSHA method also can be combined with a different model. Okay, so you can use one value and do all of them, one max, one recurrence relation, one GMP, or you can do combine several recurrence relation, okay, several Mmax, okay, several GMPs, and by taking a logic tree approach. Okay, not all the uncertainty can be described by probability distribution. Most appropriate model can be not clear, so they can take a multiple model and weigh them accordingly and combine them. For example, this is my final results I am going to expect, where I have the two attenuation model giving different weight. So equal weight I have giving two GR equation, one is the characteristic equation, another is the complete data equation, and that weightage and different Mmax you can see, okay, like that. Then finally this combined one will be taken, like you can see the weightage. So at the end the cumulative weightage should be the unity, that is what we will say, but you will try to account all the possibility uncertainty associated in this. So that kind of analysis called as a logic tree probabilistic seismic hazard analysis. So right now this, as I told you, that the writing of MATLAB code is not easy, you need a extra knowledge and skill. So because of that there are some companies who made this program as a commercial program, okay, FIS risk, risk 4A and seismic risk 3 package, where they try to incorporate regional wise GMPs, sources and model. So where you can get the hazard analysis from the package directly by understanding the what input you are giving. So that kind of models also available commercially for seismic hazard analysis. Okay, so that also can be tried. Okay. So even though this model I said it's available, you can see that DSHA, PSHA doesn't really account a regional variation, okay, because they didn't specify what is the seismic steady area you should take, which we felt, we have seen that it's very important. They didn't specify what Mmax you should take, they didn't specify what are the GMPs you should take, how to take. So all those are the, generally they are given, it's a global step, you can adopt anything. So that makes many times researchers what they do based on their experience, okay, based on their knowledge, they end up using a known information to the input, which give the some kind of output, which is not more realistically suitable to the region. So in order to overcome that, we developed a rupture based seismic hazard analysis. So the rupture based seismic hazard analysis basically, which take care of the each and every aspect of the hazard analysis by counting a proper regional input. So one of them is selection of seismic steady area. Okay. So what do we do? Basically you consider intensity, damage distribution and then RBSHA of the structure which is available in the region, and then take that as a seismic steady area map. Okay. So distance, that is the one regional input you can consider. Then once you are done that, so you to identify the best magnitude conversion equation for the homogenization. So you can take a regional available data few, like we have said on LLH, no? Similar kind of approach you can adopt and identify the magnitude conversion equation best and try to homogenize the catalog. Once you homogenize a catalog and try to prepare a seismotectonic map using the regional source and the activity of the in the region. Once you are done that, try to estimate a Mmax and regional recurrence relation. So this will basically, all these regional inputs are gone in this Mmax and recurrence relation will be more representative. So, the Mmax of each source or region can be considered from the regional rupture character, which I told you how you can obtain, that you can use. So, then identify a probable future rupture location. This identification of the probable future rupture locations are very important, which is basically the conventionally they told that wherever Mmax is there, you add increment and consider that for hazard analysis, but wherever there is no Mmax sufficiently, you will be ignoring that source. In the regional rupture character method, we give more weightage to the active location where there is a minor earthquake, but there is no big earthquake. So, that is the difference. So, that procedure and discussion you can also find in the this journal paper, which is published very recently in the engineering geology. Once you are done that, you try to characterize Mmax and hypocentral distance combination. Okay, so, from the previous steps, select a proper ground motion predictive equation and weigh them, estimate the weights and ranks based on the regional seismic data. Okay, that is the next step. Once you are done that, you do PGA estimation, and from that you identify which source and M gives a more PGA, that will be taken as a rupture based seismic hazard analysis values. So, the probabilistic seismic hazard analysis of the rupture based approach remains same up to source 1 to the step 1 to 8, but however we change in the procedures of de-aggregating the factor. For example, in the conventional approach, the alpha is considered Ln and sigma Ln, the length of the source and total length of the source. In the RLD approach, we give RLD ruptured and total RLD of the region. So, this way this alpha and this alpha is different. So, this alpha will be followed by the rupture based seismic hazard analysis probabilistic based approach, and then the number of earthquake and then total number of earthquakes. So, this gives a more weightage for the already ruptured source or already earthquake location, but here we are taking 1 minus of that. So, where it will give the weightage, but less weightage, but give more weightage to the where the number of earthquake is less. Okay. So, that concept has been introduced here. So, this is actually in the research and development stage. So, we are published up to DSHA, PSHA we are writing the paper, but this practice I believe that it will be useful. By the time you see this course, maybe we might have published this work, you can also read that paper. So, then that weight and rank difference will be incorporated in the PSHA, that PSHA become a RSHAP. Okay. So, rupture based seismic hazard analysis in probabilistic way, where you account and give more weightage to the non-ruptured location. So, let us see how this calculation works for the typical DSHA case of the conventional approach and then the rupture based DSHA approach. So, let us take a area. Okay, this is my steady area. So, I have the 5 sources. Here I am giving you the typical calculation. You do not exactly look at the size of the drawing and then estimation and all, only a typical calculation here. So, this is my steady area. This is my seismic steady area. So, the conventional approach, you do not worry about the seismic steady area because there is no guideline. Okay. But my rupture based approach, we selected this based on the past seismic data in the region, intensity map or PGA record, whatever. So, we have 5 sources A, B, C, D, and each source we have the different earthquake. So, you have small earthquakes, okay, then medium earthquake and big earthquakes in the each source. You can see that. So, these are the small earthquake which is less than 4, generally ignored in the conventional approach. So, that means the source E and D may not accounted in the hazard analysis. So, the equation above 4 is 5.3 magnitude 6.5 and 5.5 may be considered for hazard analysis in the conventional approach. You can see ABC observed maximum magnitude, since it is less than 4, generally it is not counted. So, the next is actually your number of earthquake. So, the number of earthquake basically associated with the your PSHA procedure of rupture based analysis, that is why we are taking that also to show how it varies. For example, A has a many earthquake, B has a many earthquake, C has a many earthquake, because this is from the past earthquake occurred. You can also see the period of earthquake. You can see the 1998, 2010 and 1975. So, this is about the seismotectonic map and try to understand how the data is there. Okay, we did homogenization, conversion, everything. It is now ready for hazard analysis. So, then let us see the source and the length, starting and end length, and estimate a length, and then the shortest distance to the site. Okay, using this perpendicular line you can estimate a shortest distance to the site. So, that has been also estimated using the Excel. So, once you estimate that, you need to establish a regional rupture character. So, we have seen how the regional rupture character is estimated. This is the typical plot of that, not for our case, but you can see this is the estimation. Based on this, you give a M max segment, okay, segment 1, segment 2, segment 3. So, by assuming this kind of relation, you can estimate a probable rupture length and RLD, and again convert that RLD to the MW. You can see this is the M max by increment method. So, where you can see here. So, this is the observed magnitude. I added 0.5 as a M max from the increment method. Okay. So, this earthquake is a maximum magnitude as per the conventional procedure of DSHA, but the revised M max is this one, which is from the rupture based analysis. So, now I have the M max, I have the distance, okay, I have to select a GMP. So, conventionally what I will do, so this is actually the estimated M max are overlapped in the seismotectonic map, you can see the difference. So, this I will be using in the rupture based analysis, this is the conventional approach. So, here I ignored these two sources in the conventional approach because the magnitudes are less than 4, but in rupture based analysis I do not ignore, because there is a event and there is a source which indicate that there is a seismic potential there, it may rupture in the future. So, that is what beauty of this RSHS method. So, this is the typical plot of that. So, then we will now take a GMPs known to us and then try to estimate a PGA. As I told you that the 4 GMPs we have taken, which we have discussed in the ranking previously. So, that GMPs I have a conventional method, what I will do, I will take whichever GMPs I felt it is more. For example, since I believe that my equations are good, so I take both of them and give equal weightage to estimate a hazard values. But if you do systematically and select a GMPs according to LLH approach, basically you will be ending up with these 2 GMPs. Okay. So, which is only I recommend in the rupture based seismic hazard analysis. Okay. So, this is for the rupture based. Let us see how the results are varies. Let us see the seismic source ABC, typical DSHA, because D and E we ignored because less magnitude. So, this is the M max estimated by increment, PGA for 50% percentile, PGA for the 80% percentile. So, this 80%, 50% it comes your error term variation. Okay. So, median value they give. So, you can vary for the median, lowest and highest value, you can see the PGA. From this we can conclude that out of this whichever causing a maximum one is the controlling earthquake and controlling source, you can see this one. So, basically the A is considered as a vulnerable source and the critical magnitude. Okay. This is the from the DSHA approach, but as I said that it does not account a probable future location, since your data period is very less. If you go back to the map, if you look at a time period, say I want to do hazard analysis on 2020. So, I consider the data in the last 50 years. Okay. So, but I have the return period of 100 years earthquake. Okay. 100 years the return period of my design earthquake or the average earthquake in the region. So, in that case the possibility of occurring this earthquake in the next 50 years is very less, correct, because this occurred on 2010, 1998, which is less than 50 years of the period, but I have the 100-year return period. Okay, that means if it is occurred close to the 100 years, I may give more weightage, otherwise I no need to consider this as a big important for the future earthquake. So, that kind of concept has been incorporated in the rupture based seismic hazard analysis. So, how it is incorporated, as we have seen that. So, here you see I do not give the weightage to any of the source, I will estimate M max based on the RLD approach and estimate PGA and estimate like this. So, you can see here this is the highest value, which is basically the this one, but this is a DSHA procedure where the probable location, okay, is not so much weighed. So, if I want to weigh them so much, so if I take your deaggregation factor, okay, so Nm naught, okay, so where the alpha and beta if I take from the number of earthquake, then this source, okay, the A and B will give the less weightage and the other source will get a more weightage, that reflect in the rupture based seismic hazard analysis in the probabilistic approach. Okay. So, that is the difference between the R. So, here you can see that even though the same source is considered, but the PGA values are completely different, because this PGA value indicates a rupture potential in the region, which is not accounted in the conventional way. And the GMPs are selected systematically, which also changes a value, because I selected known experience in the conventional DSHA, but in the rupture based one I selected based on the regional data. So, the values are completely different, even though source may be same, but the controlling magnitude and controlling PGA values are completely different. So, that is how the rupture based method will be more unique and more representative for any region. Recently this we applied for the our KRS dam, okay. So, where this procedure has been demonstrated, this publication you find in the engineering geology from my website. Okay. So, let us see what is the summary between these two approach. The seismic steady area, conventional approach does not talk about anything on seismic steady area. You can select whatever radius you want. Some people use 100 kilometer for the DSHA, some people use 300, some people use 400. There is no specific. But in rupture based analysis, we say that you select your seismic steady area considering the intensity value of the past earthquake radius of 4 to 5 or PGA 0.01 and above, which is interesting to the structures. Okay. Second, the weightage to the past earthquake in the future prediction, actually conventional approach, okay, they give more weightage to the already earthquake occurred location, but in the rupture based analysis it gives very less weightage, because it consider also potential possible rupture location. Maximum magnitude any suitable way, which is listed 7. Rupture based analysis highlight that you should estimate M max only by the Unbergen et al. Using the regional rupture character, which is developed by us. Considering the minor earthquake associated sources, generally conventional approach they ignore the minor earthquake, because they always take a magnitude 4 or 3.5 and above per hazard analysis. Because of that, the minor earthquakes occurrence locations are ignored. But in the rupture based analysis, we give more weightage, because we assume that it is a probable rupture location and give more weightage. So, weightage, weight and rank of GMPs. So, mostly conventional approach they do not follow any ranking system. So, and they assume based on their knowledge they take GMPs and give equal weightage or some weightage which they believe right. Who the person who incorporate a hazard analysis or do a hazard analysis or decide a hazard analysis. But here we estimate systematically, rank them and use that rank and weight for giving the GMP ranking. So, that is why these values will be different. Flexibility in calculating worst scenario. So, here the maximum you can estimate, there is no flexibility, but here you can vary the RLD percentage. By the way, you can define what is the factor you can adopt, okay, because the RLD is the mathematical number. You can adopt 1 means there is no increase, okay, 1.2 means slightly increase, 1.5 means more increase, 2 means very high increase. So, that kind of flexibility is there to handle a future fixing up worst, medium and low level requirement of the structure. So, that is one of the highlight in the rupture based analysis. So, this comparison of seismic hazard analysis conventional and rupture based analysis for DSHA will give you the insight how the hazard analysis has been done. Okay. So, with this we close the entire syllabus of the class. So, you can see that we started talking about the different hazard. Okay. So, then we talk about the seismic hazard. Okay, how it is very important, how many people die. We have seen a different seismic hazard, how to protect, okay, how to minimize that is basically try to understand the hazard, try to estimate a reliable way and educate your people. Then we also seen how the earthquakes are measured and how the engineering seismology knowledge begin in the different part and different equipments available for the earthquake measurement and the earthquake quantification, magnitude, intensity and different scale available and different earthquake record and how to convert that and how to arrive a ground motion parameter, time domain parameters. Okay, so frequency domain parameters we have seen, seismic station we have seen, seismic instrument to measure earthquake we have seen. Okay, so then with that also we have tried to understand a simple model, point source model, planar source model, simulation of ground motion, what are the models are available, predictive equation, what is the equation. So with that we also understand how the regionally seismotectonic parameter varies, seismic steady area varies, okay, how to estimate these parameters, map them and try to finally arrive hazard values for the any structural requirement. So with that we basically covered the entire syllabus of the course. I hope you learned something from this course. Okay, so I am very happy that you learned something which is useful for your career or your enhancement of the knowledge to prevent at least few death or one death due to the earthquake or escape from the earthquake. So if you need any further details and you would want to use our service or research, you please approach me. Okay, so my website IISc, like Anbalagan IISc, if you type in the Google, you can find my website. Also your phone numbers which may be available I think from the NPTEL website. So I thank you very much for watching this entire 30 plus lectures and taking this course. So I hope you got some knowledge out of this. If you need more clarification, maybe because of this video interaction, I couldn't able to interact with you. I am not very sure who are all going to take, but anyway, so you can give your suggestion and feedback. So even if you want to extend this course to next level, I was talking about the amplification estimation, liquefaction estimation. Okay, you want to extend this to that level. So site characterization like microzonation procedure, you please comment so that I can see how best I can offer this course in the future. So if you have any suggestion to improve this course, also welcome, so that I can incorporate my regular teaching in the MTech and PhD level. So I try to tell you what I learned, what I am doing. Okay, so there may be here and there some pitfalls will be there. So which maybe you can bring to the notice. I try to correct it. So your feedbacks and comments may be helpful for NPTEL as well as to improve the course in overall in the future. Thank you very much for taking this course. I wish you all the best. I also wish you all the best for final exam. I hope all of you can clear easily this course and get good grade. Already my question papers are set and supplied to the NPTEL office. Thank you very much. Thank you one and all. Jai Hind.